Hello everybody, this is the fourth and last video for chapter 4 of the statistical learning course. So in the remainder of the chapter, we will discuss two remaining techniques. The first one is local regressions, and the second one is generalized additive models. So we'll start with local regression. So local regressions are another way to incorporate nonlinearities within prediction models while still using some form of linear regression model. So this method can be seen as a mix of regular linear regression and k-nearest neighbors. We will now outline this method and describe how it works in practice. Okay, but the idea in local regressions is that when you have a new observation whose predictors are x0, you will train every time the model to so for each new observation x0, you will retrain the model based on only the neighboring data. Okay, so in the position to linear regression, where you do one regression for local regression for each value of x0, so each new possible value of predictor, you'll have to retrain the whole model. But instead of having using the entire data set, you might restrict yourself to only training data which are close, whose predictors are close to x0, so as to use neighbors or to train the model locally, if we can say. Okay, so for this method, for many methods, so for example, splines, we've discussed univariate predictors where xi was in one dimension, but now we'll go back to the multivariate case because there's no additional difficulty in explaining that directly for the multivariate case. Okay, so once again, let's say we have a training data and we have a new observation whose predictors are x0, and we want to predict the response y0 for that new observation. So how do we do that for local regression? Well, the first step is to select an integer k. So how that integer k can be decided, once again, it's through cross-validation, for instance. But let's say now we take a fixed value of capital K. We'll take the k nearest neighbors of this new observation x0. So the k observations in the training set whose predictors xi are the closest to x0. And once again, to define closest, there are many ways to do that, many possible distances, but a common way to do that is to use the Euclidean distance, for example. Okay, so you can use a Euclidean distance, you can use like a scaled version of Euclidean distance where you would scale all the predictors. This is equivalent to what we call the Malanahobis distance or something like that, where you have some weighting of the various dimensions with respect to the volatility, for instance, of the various predictors. So there are many ways to define distance. Let's now take the Euclidean distance and we say we find the k observations whose predictors have the smallest Euclidean distance to x0, and then we define the set, as we did earlier in chapter 2, as the set of all k nearest neighbors to the new observation x0. Then for each observation in the set of k nearest neighbors, so we'll denote I the ith observation within the k nearest neighbors, we will assign a weight wi0 to that observation. So wi0 represents the weight associated with the ith neighbor of the new observation 0, x0. And then we'll see how we'll discuss possible ways to assign these weights, but the idea here is the closer xi is to x0, the higher the weight should be. Okay, so we'll consider all nearest neighbors of an observation, but the closer the neighbor is to x0, the higher the weight it should have when we're going to train the model. Okay, so we want to weight more heavily observations that are more similar, whose predictors are more similar to x0. And then what we will do is we will run a weighted least squares linear regression of the responses y over the xi, so the predictors of the nearest neighbors, for all I within the nearest neighbors. So this means that the set of betas of the linear regression we're going to apply, and here the betas, there's this underscore x0, which means that every time we have a new observation x0, so predictors of a new observation, we will rerun that regression to get a different set of betas for the prediction. Okay, so for all values of x, a different linear regression is made, and the betas, or the parameters of this new linear regression, is obtained by minimizing the sum across all data points in the nearest neighbors of the weight times the squared prediction error you make. Okay, and the prediction error is your response of your ith neighbor minus here the predictors of the nearest neighbor times beta 0. Okay, so the idea here is to find the best slope for this new observation x0, we'll find the neighboring observations and we'll fit a straight line to try to match as closely as possible these neighbors. And then the difference with what we had earlier is that we will assign a weight to each of the prediction errors, where we'll weight more heavily errors associated to neighbors who are closer to x0. And then once we have that, once we find the beta x0, then the response for the new observation is predicted as the linear combination with weights being the betas and the coefficients here being, or the predictors here being the vector of predictors within x0. Okay, so the idea, if we draw a little picture to make that a bit more clear. So the idea, let's say we have some, okay, let's do something like this. Let's say we have the xi. So this is all the observation. I'll just drop the I here. These are all observations from our data. These are the responses. So let's say we have data like this, something like that. So the idea, if we have we have a new observation, its predictors are, let's say this is the x0, the value of the predictors of the new observation. Here this is in one dimension, so let's assume there's a single predictor. It can be generalized to multivariate, but let's do it in a univariate case here. So what we would do here is, if we want to predict the response for these new predictors, then the first step would be to try to identify the k nearest neighbors. So let's say we use k is equal to 3, then probably the 3 nearest neighbors would be this one, and maybe this one. So here what would happen is you would apply a linear regression and find the slope, but using only these 3 neighbors. So all of the other points you would disregard them, and you'd fit a straight line through weighted OLS. So it's almost as a regular OLS, but you assign a weight here for all errors, and then you find a straight line which minimize the weighted squared errors here. Okay, and then once you have that, you can form your prediction for the new variable. So you would, if x0 is here, then you would find the value on the straight line, and this would be the predicted value here for y0. Okay, so this is how it works. It's nothing very simple, but we see that every time there's a new x0, instead we will reperform a new linear regression. So let's say we have another value of x0, which is here. Then once again, we would find the 3 nearest neighbors, then try to find the slope here. Let's say this is the slope, and then make the prediction which falls, which would fall here in the line. Okay, so we can see that For local regression, this is called a local regression because we do a linear regression, but only locally, meaning we only use the closest neighbors. Okay, the other issue we have to discuss is the weights. So uh, instead of an ordinary, well, if we use the weights equal to 1 for all observations, this falls back on regular linear regression, but only on the nearest neighbors. But now if we add this new set of weights, so the first question is how do we determine the weights? And the second question is once we've determined the weights, how can we solve this optimization problem? Okay, so we will first discuss the first question. Uh, Once we've selected the k nearest neighbors, so okay, this first point, this is again k can be selected to through cross validation. Okay, so to select k, there's well-known techniques, but now once we've selected k, and let's say we have the set of neighbors, we have to determine weights for each of the neighbors to use within the regression. So a typical way to do that is to use Gaussian kernels, so-called Gaussian kernels, to determine the weights. Okay, so why Gaussian kernels is because this expression here, it's really the density of a multivariate Gaussian distribution. So what we can do here is we can set the weight for the ith nearest neighbor of observation x0 as so this is the density of Gaussian density of an observation xi if the mean of the density is the vector x0 and the covariance matrix of the density is sigma, where sigma is some suitably chosen matrix. Okay, so here, why does this make sense? It's because the closer xi is to x0, the smaller this expression here. Okay, so here this guy, this guy, it's known as the Malanahobis distance between xi and x0. So it's basically almost like a Euclidean distance, but we use like some matrix here to weight these distance. Okay, where here we will not discuss sigma right away. We'll do that in 2 seconds. But let's say we pick a suitable sigma, then this is some form of weighted distance between the predictors. And if xi is close to x0, this distance will be very small. And because there's a minus sign here, this whole quantity will be very larger. Okay, so we see that using the Gaussian kernels or the Gaussian density here with this expression, the closer xi is to x0, the higher the weight will be. Okay, so this is a common way to select weights in a local regression. Now, how can we select the sigma? A typical choice would be that sigma could be diagonal, so all off-diagonal elements would be 0. And the jth element in the diagonal could simply be the sample variance of the jth predictor. Okay, so this entails that all predictors would be weighted based on their scale. Okay, so if one predictor has a much higher variability than the other, then using the inverse of that matrix would entail that that variability is scaled so that all predictors are put on the same scale when computing this distance. Okay, so Gaussian kernels are one well-known way to select the weights if you want to do these kind of local regressions. But there might be other weighting schemes. Okay, but we won't discuss all possible weighting schemes. There are many possible ways to do that. This is one that makes sense. Okay. The other thing we didn't mention, and I realize it's not in the slides there, is, let's go back one slide. This is a weighted linear regression. So you might be wondering, well, this is not the regular OLS. How can I solve that? And please go see the exercises where the solution to this regression is detailed. Okay, so once again, it's possible to solve this linear regression, this weighted linear regression in closed form, and the estimator beta is known in closed form for this. Um, so please go to the slides and have a look at the corresponding exercise which derives the closed form solution for this local regression. So this summarizes our discussion with respect to local regression. So once again, uh, this chapter introduced a lot of local ways to perform predictors. So either we could come up with a local prediction function and fit once this predictive function with a local behavior, for example, cubic splines that we've outlined earlier, or alternatively, another approach to local prediction functions is that you can still use the regular linear regression or maybe some weighted linear regression, but instead on training the model once with all data points, every time you have a new observation, you retrain the model only by looking at neighboring data which are more similar to your observations. Okay, and the advantage of this is when you retrain the model with only local neighbors, then this allows discarding irrelevant data. So the assumption is that if you look at the entire pattern might not be linear, but might be locally linear. So if you look only closely at neighboring observation, then on the local scale, it might look linear. Although that on the global scale, if you look at all data points, then it would not be linear. So this is the rationale for using local linear regression. Okay, so and now we'll go to the last topic of this chapter, which is generalized additive models, which can be seen as some form of generalization of GLMs or generalized linear models we've introduced earlier. Okay, so generalized additive models will combine features of GLMs and features of let's say local regression models such as the cubic splines or splines we've discussed earlier. So this class of model, generalized additive models, it will apply to multivariate predictors. Okay, so we'll assume that for each observation there are multiple predictors for that, so p greater than 1. And the assumption underlying the generalized additive models is that each predictor have nonlinear impacts on the response. So the contribution of each factor is nonlinear. However, the total impact of all features will be additive, okay? Which means that feature 1 will have a nonlinear impact, feature 2 will have a nonlinear impact, but the total impact of all predictors is the sum of the impact of all individual predictors. Okay, so this is why there's the A in generalized additive models. It's because you add the impact of the various predictors to come up with a prediction for a given observation. So the generalized additive model has the following following representation for the mean of the ith observation. So it assumes that g, so again g stands for is the link function, g of the expected value of the ith variable given your predictors is the sum across all predictors of your data set of fj. So fj represents the nonlinear impact of predictor j applied to your jth predictor. So we can see that the impact of the various predictors are summed, but the impact of each individual predictor can be nonlinear and is characterized through that function fj. Okay, so fj is a smooth nonlinear parametric function. Okay, G, again, it's the link function. And again, we have additional assumptions, which are that given the once we fix the predictors, the responses are assumed to be independent. And once again, people typically, so this is not, you're not forced to have that, but a typical assumption is that given the xi's, the yi's follow a distribution from the exponential family of distribution. Okay, so once again, this last assumption, it's not mandatory, but it's often the case that people use that. So the here we talk about a link function, but the most well-known case is when g is the identity function, g of x is equal to x. So in this case, the g simply disappears, and you have that the expectation is the sum of these nonlinear functions. And the idea with generalized additive models is we don't want to impose a choice for f in the sense that we won't specify f is this function. So for example, we won't say f is the exponential function. Instead, we'll let the model try to learn the shape of f itself. So we do not impose our beliefs on f, we'll let the model learn f. Okay, so if we go back here, we can see how generalized additive models are generalizations of the GLMs, because if fj is the linear combination, so if fj of x is beta times x, then we fall back on the generalized linear model. Okay, so if we take all the fj's to be linear functions, then we fall back on the particular case of GLMs. Okay, so in GAM models, so I'll call them GAM models. GAM stands for GAM, or Generalized Additive Models. So in GAM models, the function fj's are learned by the algorithm itself. We do not impose a shape for fj, but we do not impose a precise shape, but rather we let fj be a very flexible function, which is parametrized, and we let the algorithm or the model learn these parameters by themselves. Okay, so typically fj of xi is some parametric function of a vector of parameters beta. So for each predictor j, there's a distinct set of parameters beta, and we'll want to learn these betas based on information provided in the training set. Okay, so the vector beta j is denoted by beta j1 until beta jpj, where pj is the number of parameters in the vector beta j. Okay, and as we said earlier, GLMs are special cases of GAM models where the jth function is simply bj times xij. Okay, so we see that GAM models are more general than GLMs. Okay, so we said, let's go back here, we said that typically in GAM models, the function fj are parametric functions, but we, in practice, the parametric functions have to be very flexible if we want to not to impose a shape on the function, but we want to let the system learn it. So a typical way to do that would be to use piecewise polynomials such as cubic splines, for example, or other types of splines as building blocks, which mean that we let fj be cubic splines, for example. Okay, so cubic splines, as we said, it's piecewise polynomial that satisfies some smoothness condition, but they still are very flexible because over all the subintervals, they can have very flexible shapes. So in that case, making the assumption that the function fj is a cubic spline is not very restrictive, because these class of functions are very flexible and can match multiple types of shapes. So a typical example that we could consider is that fj is a cubic spline, so we can assume that fj of the predictor xij is, so this is the general shape of a cubic spline we've highlighted in the previous lecture. So the sum of beta k to the predictor k. So the first three are the kind of regular order 0, 1, 2, 3 monomials. And here next we have these other sets where these other terms where this is a summation from k goes from 4 to capital K plus 3, where capital K is the number of knots, times the betas, times this function, where this function, if we recall its value, so h of x and xi was equal to x minus xi to the power 3 plus, so if we wanted to represent that function, this is xi, this is x. Sorry, I'll just try it a bit higher. So this is x, this is xi. Sorry, it's my xi is ugly, and this is h of x xi, and this looks like 0, and then you have a cubic function here. Okay, so having a cubic splines representation for a function fg j entails setting this function, and we see that this function is a parametric function where this is a linear combination of predictors, but where there are betas involved. Okay, so we see that this is a parametric function with betas, which can be expressed linearly as a function of predictors obtained through a transformation of the original predictor xj. Okay, and once again, for each j, there would be a different set of knots. So for each original predictor j, you have to select a set of knots for the corresponding cubic splines. Okay, so now comes the question of how to estimate GAM models. So for the most general case, we need to rely on numerical methods. So recall for GLMs, we said that for many cases, we have to rely on numerical methods because there's no closed form. So because the GAM models are even more general, then it's normal that also for these more complicated models, we also need to rely on numerical methods. Okay, so why is that the case? Well, first, we often have to deal with non-Gaussian distributions, which are harder to estimate. If the length function is not the identity function, this is even harder to estimate. And then sometimes there are different objective functions which differ from the least squares. So let's say the GAM model for, we have a different fj for each of predictors xj in the model. So maybe for one of the fj's, we might want to fit a cubic spline through smoothing splines instead of regular interpolation splines. So in that case, you might have a different objective function to try to fit the various fj's, and having objective functions which differ from least squares generates additional difficulty in the estimation procedure. So for all these reasons, the estimation of GAM models in the most general case can be quite involved. So we will briefly discuss some particular cases, but we won't discuss this in general. You can have, once again, courses fully dedicated to these classes of model. But I wanted to let you know that the GAM function of R allows estimating GAM models. Now I know the packages in R are evolving, and if I recall well, like maybe some of the functions don't work anymore as they did when I wrote these slides first. So it's good once in a while to, if you want to do that, to have a look at the latest update. So maybe this package is not active anymore. There's a new one, so I'm not sure exactly, but you'll have to check by yourself if this still works. But by the time the book was published, this worked, and we you could try it with examples and the labs proposed in the book. But maybe nowadays the packages have evolved, so we that one, I'm not sure if it's the most up-to-date version of the package. Okay, so we said that in general it's very hard to fit a GAM model. It can be very involved, but we'll nevertheless discuss some methods and some particular cases which can be handled more conveniently. So the most the one particular case where the GAM model can be estimated in closed form is the following. So if we have the epsilons I, so for all, the noise for all observations being Gaussian, if G is the identity function, so there's really no link function, and then if all the fj's are linear functions of parameters, okay, so if all the fj's can be expressed as linear relationships, where the betas are linear coefficients from predictors, where the predictors can be transformations of the original xj. So for example, if the predictors are cubic splines or polynomials or something like that, then in that case, we can easily estimate GAM models based on what we've seen earlier. And more precisely, we will see that you can use regular OLS regression to estimate these. Okay. So how to see this? Well, it's simple. So if yi is equal to epsilon I, the noise term, plus sum across j. So here this would be the fj of the x, but if each of the fj are linear function of the parameters, this would entail having sum across I. So let's have, instead of I, let's use u. U goes from 1 to kj, where kj is the number of betas for each j of beta u beta uj of some predictor, let's call it x tilde uj. Okay, so in that case here, we see that the GAM model can be expressed as a noise term plus a linear combination of predictors. So here, if you estimate the model through maximum likelihood, we can see that this is exactly a linear model. So this gives back the OLS regression. And you could even drop the Gaussian assumption and still use this here. Okay, no, you need Gaussian, because the reason why this is the case, it's because if the variables are not Gaussian, you might not be able to express it like this. But if the observations are Gaussian, then it means that you can express each observation as a mean vector plus the noise term here. Okay, so if you can express your GAM model, like this kind of relationship, which can be done according to these assumptions here, then we see that this is a linear model, and this can be performed through regular OLS regression. So in that case, in that particular case, if for example all observations are Gaussian, and the mean of all observations is a linear combination of some predictors. So for example, if the fj for all j's are cubic splines, then this can be estimated using a single one OLS regression, which is very good news. Okay, so this should be a very flexible model, but nevertheless not very complicated to estimate. Okay, now we'll see another approach to fit GAM methods, where the fj's are not necessarily linear functions of parameters. Okay, so Consider next the following case. Let's say that g is the identity function, but the fj's aren't linear functions of parameters. Okay, so for example, the fj's could each be a neural network. Okay, we haven't studied neural network yet. This is gonna be done in chapter 9 later on, but we're gonna see that neural networks are highly nonlinear functions of the parameters. Okay, so if the various fj's are nonlinear functions of parameters, such as, for instance, neural networks or something else, maybe a decision tree or something like that, then a common approach for fitting GAM models is called backfitting. Okay, so we're gonna discuss here this backfitting approach, which is very common to estimate GAM models. So let's assume that the GAM model has the following form. So here we see yi is the sum of predictors, the sum of contributions of each predictors, where each contribution is represented by some function fj, which we assume fj is a parametric function, but it's nonlinear of the parameters beta. Plus, here, let's assume there's a noise term epsilon I, but epsilon I could be normal or it could be non-Gaussian. So we'd like to know how to estimate this kind of model if the fj's are nonlinear functions of parameters. So the backfitting procedure, it's a numerical approach which involves sequentially or iteratively refining estimates of the various functions fj by re-estimating each one of the fj's one at a time and keeping all the other fixed to their current estimate. Okay, so we will now illustrate that backfitting procedure. So in the first iteration, in the what's coming next, L will represent an iteration which represents a refinement, sequential refinement of all the fj's. Okay, so L1 entails being the first iteration, which is the first refinement of all the fj's. So in the backfitting approach, we propose here F1 will the first iteration will consist in setting all the fj's exactly equal to 0. Okay, so we start with a very simple bad approximation, which is to set all functions fj to 0 initially, and then in subsequent iterations, we will refine them. So then for subsequent iterations, so L goes to 2, 3, 4, etc., we refine the estimates of the various functions fj as follows. Okay, so for each j is equal to 1 to p in sequence, okay, so we start with j is equal to 1, then j is equal to 2, etc., we can define the following, which is uijl being the response for the ith observation minus the f. So here it's the fj's, but for the function functions f, which we will denote fk, and here hat means that it's our current estimate. So the sum of all function fk's for k is smaller than j minus also all the functions fk's, so the current estimate of the function fk's for k is greater than j evaluated in the predictors. Okay, so let's try to make sense out of this. So we said that in our GAM model, we have that the response yi is the sum of all functions. Let's write it like this: fk over all k of xi k plus epsilon I. So this entails that, I'll use another color. This entails that you can I'll write it here, for a given j. So if we fix j, we have that if we isolate fj, so fj b of xi j is equal to yi, so the response, minus the sum for k is different than j of f k x I k. And if we neglect the noise term, let's say we neglect the noise term, we'll write approximately equal to this. And approximately equal is because we'll assume the noise term is roughly 0. So then we can see that from this, we can deduct this for all given j's. So the function fj at the jth predictor for the ith observation is its ith target minus the current is approximately the target for observation I minus the sum of all functions fk for all k different than j for predictor xik. So from that, then okay, and what I'll do, I'll have this exactly equal, and here I'll okay. So here we have this here. So if we put the noise on this side, then we have this relationship here. Okay, so we can see that if we take this relationship and we plug it here, when we take the ith target and we subtract our current estimates of all function fk for all k's except j, then when we make the subtraction, this term here, if our estimates of the function f are reasonable, are good enough, then this quantity should approximately be equal to fj of your ith observation of predictor j plus epsilon I. So if you do that for all observations I, then you have this relationship which becomes some form of univariate regression problem. Okay, so based on this, because fj is a parametric function, you can estimate from that, this becomes a univariate regression problem. So you can get an estimate of fj out of that, and this is much more simple to solve than the multivariate regression problem, because this is a univariate regression, which is easier. Okay, so it's always easier to tackle univariate regressions than multivariate regressions. Okay, now one quick note here. Why is there an L here and then L minus 1 here? It's because we assume when we calculate UIJL that for all predictors k smaller than j, their function fk were already refined in the current iteration. So the most up-to-date estimate is fl. But for all k greater than j, the estimates were not already refined in the current iteration. So the most up-to-date estimates is f l minus 1, the one from the previous iteration. Okay, but the idea when we do that is that we can define new observations where if the estimates for the various other f's are reasonably good, these new quantities can act as a proxy of the jth function plus the noise term. So this, we will memorize this and see how to deal with that next. But this becomes a univariate regression problem. Okay, so let's memorize this relationship below. Okay, so we can define the u's like this, and all these quantities are known in practice, and we have this relationship. So then what we can do is we can refine our estimate of function fj through a univariate regression by considering the u's as the responses in our regression and the xij as predictors in our regression. Because if we go back here, this is a regression model where u becomes the response, epsilon I is the noise, and here this is the prediction function. Okay, so we see that in that case, instead of having to sum across all j's for all predictors, this is a regression problem with a single predictor, so we can solve this through a univariate regression technique. And this is much easier because let's say if you have a neural network, it's much less cumbersome to solve neural networks when you have a single parameter. If you have a smoothing splines, for example, then we saw previously, or well, we didn't see, but we tipped that there were ways to solve very well smoothing splines for when you have a single parameter, etc. Okay, so these one-dimensional regressions are much easier to solve than the very large regression problems of finding all the fj's at the time. Okay, so from this, you can take this linear model, use these u's you've obtained earlier as the responses, and using this fj as the xij as the predictors, and then try to fit the best fj for this, and then this fj becomes your new estimate in that L iteration. So you can do that and continue iterating. So first iteration, you refine f1, f2, f3, f4 until fp in sequence. And then once you've refined them all, then second iteration, you refine f1, f2, f3 until fp. Then third iteration, you refine f1, f2, f3 until fp, each of them in sequence. So not of these all at the same time, but each one after the other. And eventually, your estimates of the various function f should stabilize, and once they stabilize, the procedure can be stopped. Okay, so what do we mean by stabilize? You might have a criterion where if the variation of all function f is below a certain threshold or something like that, then you can stop the procedure and say, okay, this stabilizes, so these are my final estimates. And this is how in practice you estimate your GAM through a backfitting procedure. So the backfitting procedure entails transforming your large multivariate regression problem where you have contribution for many parameters to estimate at the same time into a sequence of univariate regressions which are much simpler to solve in practice. Okay, so it's an iterative procedure transforming the multivariate regression problem into a sequence of univariate regression problems. Okay, so now we've discussed the backfitting procedure to estimate GAMs. We will end this chapter by discussing pros and cons associated to GAM models. So what are the advantages of GAM models? So GAM models automatically fits nonlinear relationships. Okay, so you don't need, so if you have a GLM, for example, okay, or yeah, let's say a GLM function, the nonlinearity stems from the choice of G, which is imposed. Okay, so you cannot be fully agnostic with respect to the shape of nonlinearity you impose. Conversely, for the GAM model, what's advantageous is that the FJs, which represent the contribution of all predictors, they are not imposed. They are learned by the model. Okay, so basically you impose, for example, that fj is a cubic spline, but the functional shape you impose for the various fj's is so flexible that it can be basically anything, and this allows the algorithm to learn the overall shape of the fj by itself, so you're not biased. You don't impose bias to your model by imposing a specific shape about the nonlinearity. You let the model learn what is the shape of the nonlinear relationship. Okay, so this is good because it's very flexible, and if the relationships between the response and the predictor is very nonlinear but in a complex way, then you might use these methods as suitable ones. Okay, so such nonlinearities, if you applied regular linear regressions, of course, you would miss them. And having more flexible models allowing for to include nonlinearities, this could improve prediction accuracy. Another advantageous feature of GAM models is they are easy to interpret. Okay, because the impact of all predictors on the response is additive. So you can look at the FJs for all predictors and see first how do each predictors um, impact the response through their contribution. And furthermore, you have that the total contribution is simply obtained by summing the contribution of all predictors. So this is pretty interpretable. And so, for example, if you are in a modeling framework where you do statistical inference and interpretability is very important, then this is another advantage of GAM models. So, and therefore, so this summability of contribution also allows you to understand the standalone impact of a single predictor on the target once you let all others fixed. For moreover, another interesting feature of GAM models is that uh, you can control the smoothness of the contributions for each parameter. Okay, so for each, you say if each of the fj correspond to the contribution of each of the predictors, but for some of the predictors you might impose, for example, a smoothing spline or something like that. So depending on which model you impose on each of the fj, so each parametric form and each the way you estimate each of these fjs individually, then you might control for example, let's say you want this variable to have a smooth impact, then you can impose that this fj has a smooth behavior. This variable, you don't necessarily care about the shape of the impact, so you can have less stringent constraints and use more flexible functions for that particular fj. So you can not only have different nonlinear impacts for the various functions, but for the various predictors, but for each individual predictors, you can control individually if you want to impose more smoothness for the contribution of this parameter or other types of constraints. Okay, so we can see that GAM models, they're very interesting models because they provide high interpretability. They can capture a lot of nonlinearities, but they're still very flexible and allowed to deal with the various parameters asymmetrically. Okay, the main disadvantage of GAM models is that the contribution of each of the parameters is additive. So there's no form of interaction built on these type of models. Okay, so if you have natural interactions between the various predictors, the like vanilla form of or like simplest form of GAM models will not capture these interactions. So what you could do if you want to capture these interactions, then you could try to add them manually as new predictors. So you can define new predictors as products of original predictors or something like that. But this can become very cumbersome because the number of parameters in a GAM model can be very large. So for example, if you have a smoothing or just a cubic spline for all the FJs, then for all FJs, let's say you have 50 knots and you have 4 predictors, this ends up being 200 parameters. Okay, so this is enormous. So adding interactions, this would like add the number of an incredible amount of new parameters, and this might not be desirable. So if you have interactions to capture, maybe GAM models might not be the best, because adding these interactions might lead to a high number of new parameters and might cause overfitting. Okay, so one point I haven't discussed here is the very large number of parameters. So if you don't have a lot of data points, then it's very easy to overfit a GAN model if you because of the very high number of parameters. So it might not be desirable to use GAN models if you don't have a lot of observations. Okay, so moreover, if you have interactions, this is another thing. There are ways to generalize the GAN models by having the various FJs being functions of more than one predictor instead of a single one. But this is another generalization of GAN models, which are already pretty general. So we shall not go into these generalizations in the present course. But I nevertheless wanted to let you know that it's possible to even generalize GAN models where the FJs can be functions of many predictors, and then this can be a way to tackle interactions, especially if you have many observations. All right, so we end this chapter there, and I'll see you next time for the next chapter.